Hello all, welcome to my course on methods of adhesion measurement, theory and practice. So, we are discussing about stress and strain analysis, and today we will continue that discussion, and then we will start a new topic today if possible on contact mechanics. So, little short summary of the last lecture. So, there we discussed about the stress tensor, and we said that these are the symmetric matrix, stress tensor symmetric matrix, and x axis is a force along x axis per unit area of a surface that is perpendicular to the x axis. So, it is a normal stress along the x axis, and then x y, this is a shear stress along the x axis, but that acts along on the surface that is perpendicular to the y axis. And we also showed that x x plus y y plus z z, this is invariant with respect to the coordinate transformation, and so therefore, this is called the hydrostatic pressure minus 3 p. We also derived the stress equilibrium relation. So, that is given as x del x x by del x plus del x y by del y plus del x z by del z plus rho x is equal to 0. Here capital X is the body force. So, in absence of any body force, we have only these three terms, and this body is at equilibrium. So, therefore, no acceleration term there. We applied the used this Hooke's law to have a constitutive relation between stress versus strain, and we showed that this is the expression here, and this delta is the called the volume strain, that is E x x plus E y y plus E z z. Here this lambda and mu, these are the elastic constants. We showed that the 36 constants that we require for the generalized Hooke's law, that can be reduced to only 2 constants, and then we have derived this the expression for Poisson ratio, and we showed that the Poisson ratio is given as sigma here, that is half of lambda by lambda plus mu. So, we showed that the bulk modulus can be represented by E by 3 into 1 minus 2 sigma here, and for an incompressible material sigma is equal to 0.5, and in which case the bulk modulus k goes to infinity, and so what it means, this is an incompressible material. We also derive this particular expression for the E, that is the Young's modulus is equal to 2 mu into 1 plus sigma. So, here this is the stress tensor, and I want to say it at the today itself, at the beginning itself, that in some books and in some portion of my lectures, also in my course also, I will use this particular notation for representing the stress, but I can also use this notation. These are basically same. So, here capital X is a sigma x x. So, these are basically same. So, sigma x x means that the stress that acts along the x direction on a plane that is perpendicular to the x axis, and which is basically same, is equivalent. Okay. So, this can be used interchangeably, and some books use capital X this kind of notation, some books use this notation, and in my course also I may have changed somewhere, I may have changed these notations, I have changed it interchangeably, but you please do not get confused, this is the same thing actually. So, today I would like to take a problem. So, the problem is very simple. Let us say the Young's and shear modulus of a certain soft material are estimated as 3.5 megapascal and 1.17 megapascal respectively. So, we can obtain the Poisson ratio. So, here this Young's modulus given as E is equal to 2 into 1 plus sigma into mu, and so therefore, Young's modulus is 3.5 megapascal. So, 3.5, 1 megapascal is 3.5 10 to the power 6 pascal. So, 1 MPa, that is equal to 10 to the power 6 Newton per meter square or pascal, same thing. This is equal to 2 into 1 plus sigma, this is the Poisson ratio, into mu is equal to 1.17 megapascal, and so therefore, sigma is equal to, it will be is equal to 3.5 divided by 2 into 1.17 minus 1. So, we can actually estimate that, calculate that using calculator and all that. So, I have done all this. So, this comes out to be sigma comes out to be 0.4957. So, this is the Poisson ratio, and we can obtain the bulk modulus k from this particular relation E by 3 into 1 minus 2 into sigma. So, this gives the bulk modulus to be like this. So, this is a simple problem to demonstrate the relation between E and mu. We can also use similar expressions for finding an alternate expression for the strain energy density function. So, over here this W is the strain energy density. So, it is energy per unit volume, elastic energy stored per unit volume inside the body, and that is given by this. So, this we have presented earlier, and so here we can actually use we can write this expression in terms of the stress component. So, how do we do that? That is what I would like to show you. So, here x x is equal to lambda into delta plus 2 mu E x x, and y y is equal to lambda into delta plus 2 mu E y y. So, let us here substitute for E x x and E y y and like that. So, this is x. So, E x x will be equal to this is x x minus lambda into delta by 2 mu, right, 2 mu plus y y into it will be y y minus lambda into delta by 2 mu plus z z equal to z z into z z minus lambda into delta by 2 mu plus it is 2 x y and small e x y, that will be equal to x y divided by 2 mu plus 2. So, let me yeah, that is fine, y z equal to y z by 2 mu and plus 2 z x. So, z x will be E z x will be z x by 2 mu like this. So, like that. So, therefore, we can write it as half of into 1 by 2 mu into, let us say it is x square. So, x square plus y square plus z square, x square like that, and then yeah. So, this is fine. So, 2 mu I have taken outside, that is fine, and then minus this is lambda into delta into, let us say this is x x plus y y plus z z, and then here plus this is, let us say 1 by 2 means already taken, I have taken out. So, this is not required. So, let us say 2 into this is x y square plus y z square plus z x square like that, like this, and this delta can also be replaced, and so that is what I have done over here. So, here this delta is there. So, this is what we can get. So, after taking all these terms together, so we can get something like this. The delta can also be now replaced by this quantity x x plus y plus z plus 3 lambda plus d mu. So, if we do that, so then it will have 1 by 4 mu into this minus this will be lambda by 4 mu into x x plus y y plus z z whole square into 1 by 3 lambda plus 2 mu like this. And we can also, this is 1 by 4 mu, yeah. So, like this. Now, this lambda by 4 mu here, 4 mu here, and this is 1 by, right. Okay. Now, this lambda by 3 lambda plus 2 mu, that we can yeah. So, we get something like this, and then we can write this lambda by 3 lambda plus 2 mu also. We can find out a relation for that. So, here it is 2 sigma is equal to lambda by lambda plus mu. So, lambda by mu, that will be equal to 2 sigma by 2 sigma minus 1, and so therefore, lambda by 3 lambda plus 2 mu. So, that will be equal to here lambda by mu by 3 into lambda by mu plus 2, and so this is equal to 2 sigma by 2 sigma minus 1 into 3 into 2 sigma by 2 sigma minus 1 plus 2. So, you write it like this, and now you simplify it, and once you simplify this, we get here sigma by 1 plus sigma. So, this lambda by mu, this particular term, it is like this, and so here finally W is equal to 1 by 4 mu, and we have here these terms that we already have, minus we have here sigma by 1 plus sigma into x x square plus y y square plus z z square plus all these terms are there, and then you simplify this, simplify the whole thing, then we have 1 by 4 mu, and then you can simplify it. So, the simplified form finally comes out to be like this here, here like this. So, x square plus y y square plus z z square, and then this, and minus sigma by 1 minus sigma, and like that, and now we can further take these terms together, and this is little algebra, and that comes out to be like this. So, we can take terms together. So, I have done all the steps here, you can follow it, and finally we will get like this. So, this is the expression of W. So, that is the strain energy density function in terms of this stress components. So, x x y y z z and x y y z and z x. So, in some problems maybe the stresses are defined, okay, strains are not defined. So, we need to calculate the strain energy. So, we can actually make use of this expression. So, now let us say that we have this incompressible material. So, how the stress strain relations that change, that is what I would like to show here. So, here we can write it lambda into delta plus 2 mu E x x. So, that defines this x x s. So, delta is defined as the volume strain. So, volume strain is hydrostatic pressure divided by the bulk modulus. So, therefore, this is delta is equal to minus P by K here plus 2 mu E x x. So, here we write it like this, and then lambda by K is the relation. So, that if we work out, it will come out to be like this. So, this is not difficult to derive. So, it will come out to be like that, minus P 3 sigma by 1 plus sigma, and since this is an incompressible material, so therefore, sigma is equal to 0.5. Sigma is equal to 0.5. So, you write over there, substitute over here, you will get x x is equal to minus P plus 2 mu E x x. So, that is the relation between this normal stress x x with the E x x for an incompressible material. So, it is through this hydrostatic pressure defined by minus P. So, x x is equal to minus P plus 2 mu E x x. Similarly, if you have y y, it will be minus P plus 2 mu E y y, and z z will be minus P plus 2 mu, okay, E z z. It will be like that, and we already have the relations for x y. So, that is equal to E x y into 2 mu into E x x E x y. So, x y, these relations are already there. So, that will hold. So, that is 2 mu E x y like that. So, those expressions shear stress components are like this, that are already there. So, how the stress equilibrium relation that will change. So, here stress equilibrium for an incompressible material, okay, like this. So, here incompressible relation is E x x plus E y y plus E z z, and we can also write E x x del u by del x, E y y del v by del y, and E z z del w by del z. So, here we can substitute for x x this particular kind of relations that we derived here, minus P plus 2 mu E x x. So, if we do that, it will be something like this. So, del by let us say del x minus P plus 2 mu, okay, and now instead of E x x I write directly del u by del x. I can do that, plus here I write it as del by del y, and let us write x y. So, x y I derived it here 2 mu E x y. So, let us write it here 2 mu E x y. So, instead of E x y I will write it as half of del u by del y plus del v by del x plus del x z. So, del by del z, and here I will write 2 mu into half of del x, it will be E x z. So, E x z is half of del x, so del u by del z plus del W by del X, and that is equal to whole thing that is equal to 0. So, if you now further elaborate this, then it will be minus del P by del X plus 2 mu, and we will have here 2 mu, yeah, and we will have here del square u by del x square. We will also have here 2 mu. So, 2 let us say 2 over here, this 2, let us get rid of this 2 here. So, mu into this, right. So, 2 into del square by del x square plus over here it will be del square u by del y square plus del square u by del x del y plus here we will have del square u by plus del square u by del z square plus it will be del square w by del x, sorry, del x del y, here del x del z, del square w by del z z, like that, del square u. So, it is del square v actually, del square v by del x del y, like that. And we can actually use in that expression, okay, this expression as well. And finally, if we use this expression del u by del x plus del u by del y plus del u by del z, we can make use of that expression over here, and by that we can show that it will come out to be del p by del x is equal to mu into del square u by del x square plus del square u by del y square plus del square u by del z square. So, you just take all the terms here together, in the sense that you find out del by del x into del u by del x plus del u by del y plus del y. So, it come out to be this, and we can actually find out something like this. So, the stress equilibrium relation for an incompressible material can be written something like this, and this kind of equation we have already seen in fluid mechanics as well. So, here this is the equation. So, for incompressible material, when you use stress equilibrium relation, we will actually use this. Now, let us say on particular approximation, what is known as the plane strain approximation, and then there is another expression for the approximation, that is called the plane stress approximation. So, in the case of plane strain approximation, we are basically dealing with a, let us say, rod like material, so which is infinite in this y direction. So, since it is infinite y direction, so no strain develops there. So, therefore, all the strain that remains in the x z plane. Okay. So, therefore, it is called the plane strain approximation. So, the body is actually too long, and therefore, in the not z, no, this wrong here, this is not z, y direction. So, therefore, it is there is no strain that develops in this body in the y direction. So, therefore, this E y y, E x y, E z y, these are all equal to 0. So, since these are equal to 0, so we can write down this, we can find out from here is we putting this E y y, E z y, E x y is equal to 0, we can show that this equation, therefore, we will have only these two relations only we need to worry about as far as the stress equilibrium relations are concerned. Del p by del x is equal to mu into del square u by del x square plus del square u by del z square, and del p by del z equal to this, and this is the incompressibility relation. So, plane strain approximation, okay, will be used in this particular course a lot, and this is because of the simplification, okay, that we can obtain by this. Similarly, there is another approximation, what is known as the plane stress approximation. So, in the case of plane stress approximation, what we have is basically a thin plate. So, in the thin plate, in the x y plane, and this is y, and this is the x direction, this is the y direction, x y, and the z direction is perpendicular, and this is a thin sheet, and so inside the this elastic sheet, okay, the stresses do not develop in the z direction. So, therefore, the stress is actually 0, and the stress remains at the plane of this particular material, this thin sheet, and so therefore, this zx, zy, zz, this is equal to 0, and we can then derive the expression that will be that we can write with the stress strain relation for this case. So, here for example, that xx is represented as minus p into lambda plus 2 mu xx, and the lambda comes out to be can be represented here like this, minus p into 3 sigma by 1 plus sigma, okay, for a general relation for a compressible material, and this 3 p is equal to this. So, therefore, we can actually write here x x and then plus, and let us say it is sigma by 1 plus sigma into 3 p. So, plus 3 p, right. So, here we will have z z equal to 0 here. So, we will have 3 p, okay. This is equal to 2 mu u x x. So, here this 3 p is equal to minus of x x plus y y, okay, because from here. So, therefore, we can see that this will be x x into 1 minus, it is sigma by 1 plus sigma minus, and this is minus, this is sigma by 1 plus sigma into y y, that is equal to 2 mu e x x. And from here we can show that this is equal to x x 1 plus sigma, so x x, yeah, minus it is sigma into y y, that is equal to 2 mu into 1 plus sigma into e x x, and 2 mu plus sigma is equal to e. So, this can be written as e x x like that. So, you can derive and relation between stress strain relation from this for this particular case like this. So, here we can like E x x is equal to, therefore, 1 by E x x minus sigma y y. We can write down for similarly for E y y, we can write the equation like this similar to this expression. So, let us take a small problem here. Let us say thin rectangular plate or dimension 200 meter by 100 meter, it should be 100 meter and thickness 2 millimeter is subjected to tensile stress of 150 MPa along x direction and the compressive stress of 50 MPa along the y direction. No shear stress is applied. So, basically what we have is this, this is the x axis and this is the y axis, and so along this there are stresses which are applied. So, this is about what is the 150 MPa. So, this is 150 MPa. So, let us say this is x x and this is y direction. Now, the compressive stress along the y direction. So, therefore, the stress is along this direction. So, here y y, this is equal to 50 megapascal. So, this is 50 MPa and we should have negative sign here. So, now no shear stress applied. The Young's modulus and the Poisson ratio of the material is given 200 gigapascal and 0.3, 0.3 is the Poisson ratio. So, therefore, you need to obtain E x x, E y y and E x y. So, E x x is equal to 1 by E into x x minus sigma y y. So, E x x is equal to 1 by E into x x minus sigma into y y, right, yeah, minus sigma into y y, and so therefore, this is equal to 1 by, and the E is 200 gigapascal, 200 gigapascal is 10 to the power 9 here, and x x is equal to 150 megapascal. So, it is 150 here minus sigma is equal to 0.3. So, 0.3 into y y. So, y y is 50. So, this is minus 50. So, E x x is equal to, comes out to be, it is 150 here and for 300. So, 300 by 200. So, it is 3 by 2 10 to the minus 9, right, no, 10 to the power 6 here I have to write, because this is megapascal. So, x is a megapascal 10 to the power 6 here. So, it is 10 to the power 3 here. So, it is 150, this is 15. So, it is 165. So, 165 it will be. So, 165 by 200 and this is 10 to the power minus 3. That should be the kind of strain that we are talking about over here. So, I hope I did it right. So, here it comes out to be about 0.00825. Similarly, E y y, okay, in the same way we have to do, remember that y y is equal to minus 50 here and minus sigma, it is minus 0.3 into 150 here, okay, into 10. So, megapascal, so 10 to the power 6 here and gigapascal is 10 to the power 9 here. So, it will come out to be like this. So, we can also write down E x y is equal to 0 because there is no shear strain here, and we can also obtain the change in length along the x direction. So, that is delta L x is equal to L x into E x x, and that will be like this, very simple. So, 200 is the dimension on the x direction. So, 200 into E L x into E x x, that is a change in the length delta L x. So, that is equal to this. So, we can use this stress strain relation that we have derived here, okay, to estimate the strains over here. So, this is what we have the first few initial topics that we needed to cover to now actually start the actual idea about this adhesion measurements and all that. And one of the most important, okay, thing that we need to talk about is called the contact mechanics. So, what exactly it means is something like this. So, suppose that we have got what is known as this a cylindrical punch, right, and this punch is is brought in contact with this, let us say, a soft material. So, let us say this is basically an adhesive that we are talking about. So, this is this sponge. So, we bring it in contact and let us say apply some amount of pressure, and so there is some amount of deformation that happens. So, we are interested to know what is the kind of deformation that happens. Okay. Now, this is the load that is applied onto this. So, there will be deformation. Now, let us say the load is pull off load, this is not the compressive load. So, this is actually the pull off load. So, then you want to know if there is an adhesion between these two surfaces, what is the pull off load that is required, okay, to separate for a some amount of adhesion between these two bodies. So, now this so we need to know for that what is the kind of stress profile that occurs, okay, at the contact area. Or let us say that instead of having this cylindrical punch, we have got this kind of flat punch. So, we have this cylinder, but the surface is flat, and now we bring it in contact. So, there is a adhesion between this material and this material, and so therefore, when you try to pull it, so this remains stuck to it for some while and then it separates. So, we want to know that for a given amount of adhesion force between at this particular interface, okay, what is the amount of force, pull of force that we need to apply in order to separate it. So, we can have this kind of different kind of geometry, cylindrical punch, flat circular punch, and we can also have, let us say, flat rectangular punch. So, rectangular punch means that this particular case in this direction, this is a kind of plane strain approximation, that in this y direction, okay, this is infinite. So, as a result, these forces does not change with respect to the y direction. So, we have first brought it in contact and then we are trying to separate it, and what is the kind of force that is required. So, these are different type of situations that will occur in adhesion. So, we need to know that when we apply, okay, certain amount of load on these different types of contactor, okay, onto an elastic material, what is the kind of stresses that that develops at the contact area. Okay. So, that is what we will like to study now, and that forms our content of this contact mechanics course. So, another example is known as the probe tape experiment. So, I would like to show you here there is a typical curve that happens. So, we have this particular probe and then we first bring it in contact. So, when it bring in contact, surplus means contact, and as we press it, so the load decreases over here. So, this is basically the compressive load. So, it is negative over here, okay, and then negative, and now we try to pull it off. So, you will see that there is a pull of force that is required to separate it. So, you then try to separate it, and finally, then when you try to pull it, it remains in contact for some time, and then there is a crack that kind of propagates, and then this particular probe separates out over here. So, we want to see this whole history of this loading and unloading. So, in order to all these kinds of problems, the interesting idea is that what is the kind of stresses that develop, okay, at the contact line, and how that varies with respect to when you pull this probe from this particular layer. This soft layer can be an adhesive, for example. This is another example over here, that what happens at the contact area. It seems that the contact area may separate very easily as a single contact area, whole area, but it can also form this kind of small cavities. Okay. So, for a different situation and different kind of soft materials and like that. So, these are all topics of this adhesion, and we will go through very basic aspects of all these problems. So, the questions that actually we will ask is that how does the geometry of the punch affect pull off load? Then what is the stress profile at the contact area between the punch and the adhesive? Then how does the deformability and the thickness of the adhesive layer affect pull off load? So, deformability means that it is a, let us say this is an elastic, soft elastic material, okay. So, what is the Young's modulus of that, Poisson ratio of that, and how that affects this pull off load, or let us say the thickness of the adhesive layer. Now, how does the above pool of load gets affected by the slip no slip condition at the contact between adherent and adhesive. So, over here when this particular crack propagates, then at that time there is a normal, there is not only normal pulling, but also there is a shear that happens. Okay. So, that shear happens because of the friction. So, how does that, it is not only the normal pulling, but the friction that is also becomes important. So, how does the slip and no slip or the friction that affects the contact between adherent and adhesive, and how do undulations of the adhesive surface affect pull up load? This is important because not all adhesives or adhesive surface will be completely flat, there will be undulations, topographical undulations. So, how does undulation affect this pull of load that is required to separate this sponge from this surface? So, these are the questions that we will like to go through or answer or address in this particular course in the next few lectures in this course. So, today we will end here. Thank you for your kind attention.